Hello everybody. Today we're going to be talking about how scientists use bubbles to model atomic defects in materials back before we had microscopes powerful enough to actually see what was going on. Just a warning, we're amateurs. Our bubbles aren't as useful as the real deal. So, we've used some footage from a 1952 movie to show you how it would look if we knew what we were doing. Also, we found out after the fact that my phone's slow-mo camera operated at a similar frequency to the light bulbs in the lab. So most of those shots are stroby. Sorry about that. First off, vacancy defects are defects in a crystalline structure where the site an atom would usually inhabit is empty. The missing atom causes nearby atoms to fall into the void created by its absence. In the case of our bubbles, this meant filling the hole fairly rapidly. In the 1952 video, these voids are much more resilient and allow the scientists to explore their interactions, which we'll get to later. Next, interstitial defects are defects in the crystal structure where a small atom has managed to squeeze in between the larger atoms making up the rest of the structure. It can be a bit difficult to demonstrate a single interstitial defect with bubbles, so here's a model using the Vesta software, showing a small atom wedged in between the normal atomic sites. Substitution defects are defects where an atom in the crystal lattice has been replaced by an atom of a different element that would normally inhabit that atomic site. The difference in size between the normal atom and substitute atom determine how this affects the lattice. A larger atom pushes nearby atoms away, lengthening their bonds, and a smaller atom causes the surrounding atoms to shift inwards. Dislocations occur when atoms are displaced one-dimensionally, or along a line, like an entire row of atoms being in between the normal atomic sites. Bubbles are particularly good at modeling edge dislocations. Here you can see where the extra line of atoms starts, pushing aside the existing rows. In order to determine the magnitude and direction of the distortion caused by these dislocations, draw a line near the start of the dislocation, counting the atoms. Then, draw more lines using the same amount of atoms and following the crystal structure and fully enclosing the start of the dislocation. If done correctly, the endpoint will not be in the same point as the starting point. The extra or missing line shows how far and in what direction the lattice has shifted, and is called the Berger's vector. Substitution defects are particularly difficult for dislocations to shift past, and can rapidly cause dislocations to stack up on themselves.
So grain boundaries are areas in a polycrystalline material where the crystallographic orientation of the atoms on either side of the boundary are different. The angle of this orientation determines whether or not you have a high angle or small angle grain boundary. If the angle of the orientation difference is greater than 11 degrees, this is what is known as a high angle grain boundary. If it's less than 11 degrees, this is known as a small or low angle grain boundary. This is shown on the bubble raft as different lines of the bubbles as they curve as you look at the raft. These boundaries usually result from the collection of dislocations along the grain boundary. The dislocations found in our bubble raft are all edge dislocations because it's a 2D plane. These edge dislocations are caused by interstitial and vacancies in the bubble. Dislocations segregate along the boundary lines in order to result in a lower boundary energy in our polycrystalline material, or bubble raft as shown in this model. If we apply a stress to the edge of this bubble raft, we'll see that boundaries will react to this stress and may result in this boundary going to the edge of the raft where it may disappear. Grain boundaries may also combine as a result of this stress to form new boundaries.
Alright everyone, thanks for watching, and don't forget to like and subscribe so I can get those sweet YouTube bucks. I'd like to give a special shout out to all of you who follow me on Patreon. Your support is going to get me the money I need for a PhD. Thanks for watching.